Hey guys, welcome back to another video. Today we're going to be dealing with roots. We're going to be adding, subtracting, multiplying, dividing, and rationalizing all of our rational expressions, our roots. Now, I'll leave in the description below my last video about exponents because this sort of refers to some stuff, but if you're solid on your exponent laws and your rational exponents, this should be a piece of cake. Now, let's start off with this right here, square root of 27. What we want to do whenever we have something like this, to simplify it, what we want to do is, first things first, we need to look at our root. In this case, it's a square root, but sometimes it'll be a third root, and I'll cover that in the next example. But here, it's a square root. So immediately what we want to start thinking of is, okay, what are our perfect squares? Well, we have 2 squared, which is 4, 3 squared is 9, 4 squared is 16, and so on. So as soon as we see this, we think perfect squares. If it was a 3, we'd think of our perfect cubes. So 8, 27, 64, so on. Now, after we've evaluated this and thought of our perfect squares, we need to look at the 27 on the inside. And we're actually going to rewrite it. Now, how do we rewrite 27? Well, let me give you an example. 60 can be rewritten as 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and so on, right? These are all different ways of rewriting 60. Now, the trick is when we're doing this is once we've established our perfect squares in this example, we need to rewrite 27 using one of our perfect squares. So one way to do this is first just write 27 as many ways as you can. So there's 1 times 27, there is 3 times 9, and that's pretty much it. We don't really have 2, 4, we don't have anything else we can do. Now, of these two, which one includes a perfect square? Now, remember, our perfect squares are 4, 9, 16, 25. This one does. So, our next step will simply be just rewrite it. Just like that. Now, what we do from here is this 9 right here, we're basically going to take it out and we're going to take the root of it to give us 3 root 3. Now, what did I just do? I'll show you. Basically, what just happened was, we know that when we have, for example, square root of x, it's equivalent to x to the power of 1 over 2, correct? Perfect. So we're basically going to do the exact same thing here. It becomes 3 to the power of 1 over 2 times 9 to the 1 over 2. Correct? Basically, it was just, we went from 3 times 9 all to the power of 1 over 2, and we ran the exponent through, as we do with our exponent laws. So, now we're given this, which equals square root of 3 times square root of 9. And we know the square root of 9. The square root of 9 is equal to 3. Just like that. So then, we get the same answer. 3 times root of 3. Just like that. And that's how we do stuff like this. Now, is this mathematically correct? Yeah, it is, and I can prove it to you. Okay? So I just rewrote this now as 3 to the 1, basically, because it's an imaginary 1, times 3 to the 1 over 2. Now, these have the same base. So, what do we do to our exponents? Well, we add them. So it becomes 3 to the power of 1 plus 1 over 2. And well, 1 plus 1 over 2, if you remember adding fractions, we want them to be the same denominator. So we get 3 to the power of 3 over 2, just like that. Now, if you remember how to turn this into our rational form, what we do is the denominator becomes our root, and the numerator becomes our exponent on the inside, just like that. And well, if we simplify this, we get square root of 3 to the power of 3 is 27. just like that. Notice how this and that are the exact same. And well, this and this are the exact same, so that and that are the exact same, just like that. Now, this is how we do it, and I'll give you another example, but I'm going to use a root of 3 in that one, just to give you guys a feel of how to do it. Okay, so here we have the third root of 81. Now, same steps as before. First thing, we want to look at the root. It's 3. So immediately we should be thinking of perfect cubes. They are 2 to the 3 is, well, 8. I'll write them down. 3 to the 3 is 27. And 4 to the 3 is 64, just like that. Our next step is to break up 81 into one of these. So what is another way of writing 81? Well, we have 1 times 81. We have 3 times 27. We have 9 times 9. And I'm just going to stop there because it just loops back. Now, of these 3, which one of them includes one of our perfect cubes? This one does, 27. So our next step is simply going to be rewrite it. 3 times 27, just like that. And then from here, basically what we're doing, and you don't need to show all the work that I did in the last step, you can simply go from here and say, okay, well, the third root of 3 remains third root of 3, and the third root of 27, well, we know is 3. So it becomes 3 times the third root of 3. And the way we did that is, well, we took the 27 out by taking the third root of it. So those right there are equivalent expressions. Now let's jump into a couple examples, and then afterwards we'll work with multiplying, adding, dividing, subtracting. Okay, right away, first 3 examples. So square root of 60. Now, what are our perfect squares that we know could potentially multiply to 60? Let's see, we know 4. 4 times 15 actually works. So let's just rewrite that as root of 4 times 15. And now from here, we can take the 4 out by taking the square root of it, and we get 2 times square root of 15, just like that. That is our simplified answer. Let's move on to this one. Now, this one has a 4th root, so it's a bit different. We need to think of all of our exponents of 4, and I'm just going to write them out. We have 2 to the 4, which then gives us 16. We have 3 to the 4, which is 81, and I'm just going to leave it at that. Now, of these 2, can we rewrite 160? Yeah, we can actually. 16 times 10 seems to work nicely. So we get the 4th root of 16 times 10. And then from here, we can't take the 4th root of 10, so we're going to leave it as it is. But we can take the 4th root of 16, and it's 2. So it becomes 2 times the 4th root of 10, just like that. Finally, let's do our last one. Now this one's a little bit different because we have something on the outside already there. But it doesn't really have to change our process at all. All we're really going to do is multiply this now by whatever we take out. And I'll show you that. So let's take a look. It's the third root of 24. And we know our perfect cubes, 8, 27. So it can't be 27, it has to be 8. So it's 2 times the third root of 8 times 3 gives us 24, right? So then from there, all we're going to do is we're going to take the 2 out of this thing by taking the third root of 8. So we get 2 times the third root of 3, just like that. And now this 2 multiplies by that. And we'll get into multiplying our, what are they called? Our rational expressions quite soon. I think it's actually the next example. But simply when you don't have a rational expression in front of something and you multiply by 1, all you're doing is multiplying the front coefficient. So now we get 4 times the third root of 3, just like that. Let's move on to the next couple examples. Okay, moving on. Example number 4, 6 times the square root of 160. So we want to rewrite our square root of 160 just like that. Now, what are our perfect squares? Well, we know we have 4, we have 9, we have 16, and we have 25. 16 actually works really nicely. 16 times 10, right? 16 times 10 gives us 160. So then from here, we can take the 16 out by taking the square root of it. So it becomes 4 root 10, just like that. And now, just like the previous one, 6 times 4 is 24. And we keep the root 10 the way it is. Next up is this one, 5 times root 54. Now, once again, it's a root. What are our perfect squares? 4, 9, 16, and 25. This one looks like it has 9, right? 9 times 6. So, square root of 9 times 6, just like that. And then we get 5 times, well, what's the square root of 9? It's 3. And root 6. And then from here, 5 times 3, just 15 root 6, just like that. Moving on, we have this one. Now, this one is a little bit different because you might not see it right away. So, let's try to look for it. Square root of 729. Well, we know what that is, actually. It's 27. So, we know our answer just becomes 54, just like that. Okay, moving on to our last 3 now. Now, we can actually add variables when we do this. And the way we look at it then is we try to split the variable up accordingly. So, for example, x to the 5. Well, we know that when we add exponents, when we multiply exponents, we add the exponent, right? For example, x to the 5 could be x to the 3 times x squared, right? Or it could be x to the 1 times x to the 4. Could be anything like that. So what we try to do is we try to match one of them with our root. And you'll see what I mean by that. So here, for example, it's already given to us as in x squared. So now all we really want to deal with is the 72. So let's think about it for a second. Perfect squares. Well, we know 9 times 8 is 72. So we're going to rewrite it. 9 times 8 times x squared. Now from here, can we take the square root of 9? Yeah, we can. Becomes 3. Can we take the square root of 8? Unfortunately not. So 3 root 8. And can we take the square root of x squared? Yeah, actually we can. It just becomes x. So now let's rewrite this. 3x root 8. Now, is that fully simplified? No, it's actually not, because root 8 can be taken down another step. We know that 4 is a perfect square, and 4 times 2 is 8, right? So we get 3x root 4 times 2. And then from here we can take the square root of 4, which gives us 3x times 2 root 2. And just like that, all we do is multiply 3x by 2. My apologies, the camera died. Anyways, as I was saying, from here we can actually just go 3x times 2 and we get 6x root 2, just like that. Now, we didn't have to do all the extra steps that we did if we had just realized at the beginning that 72 could have been written in a different way. We could have written root 72 as root 36 times 2 times x squared. And just like that, well, root 36 is 6, root 2 stays root 2, and root x squared becomes x. And just like that, we could have skipped all those extra steps and went straight to the answer in half the amount of steps. That's why it's always important to, at the beginning, try to get the biggest perfect square you can. Otherwise, you're going to keep going and going and going, just repeating yourself. And yeah. Okay, now let's do the next. Negative 8 times the square root of 24 times k to the 3. Now, what I was saying earlier is we want to rewrite k to the 3 to satisfy our root. So in this case, it's a square root of 2, and we can rewrite k to the 3 as k squared times k. So just like that, that's how we're going to rewrite it. We get negative 8 times, and the 24 can be written as, well, 4 times 6. So 4 times 6 times k squared times k. Just like that. And then from here, we get negative 8 times square root of 4, well, it's 2. And the square root of k squared, well, that's just k. And then we can't take the square root of 6 or k, so we leave them in there. And then from this step, we just multiply the negative 8 through to give us negative 16k times the square root of 6k, just like that. Okay, the last one is 2 times the square root of 8 times p squared times q to the 3 times r. Same thing that we've been doing the whole time. 8 can be rewritten as 4 times 2. P squared, we actually want to keep it the same because we want our exponent to be the same as the root, in this case, squared. Q to the 3, we want to rewrite it as q squared times q, and r, we just want to keep it the exact same way it is. We can't really do anything to it. From here, all we're going to do is take the square roots of everything. So square root of 4 becomes 2. Square root of 2, can't really do anything. Square root of p squared becomes just p. Square root of q squared becomes q. And that's it. We can't do anything to anything else. So we just write it in our root. Now don't forget that step. We missed 2, q, and r. So 2, q, r. And now from here, all we're going to do is multiply 2 by this. And our final answer becomes 4pq root of 2qr. Just like that. Now let's move on to multiplying, adding, subtracting, and dividing. Okay, so now let's talk about adding and subtracting our rational expressions. And right here I have an example is 4 times the square root of 6 minus 3 times the square root of 6. Now you might not know how to do this, or you might. Either way, let me help you by giving you something that should make it a little bit easier. If I say x equals root 6, just like that. Now let's just rewrite this. It becomes 4x minus 3x. Well, we know how to do that, right? It just becomes x. How do we know? Because we did 4 minus 3, and we didn't touch the x at all. And essentially, that's it. That's how we add and subtract our rational expressions. Now, the trick is, because it does get harder in the examples I'll show you, the trick is we want to get our roots to be equal. If this was, for example, 3 root 5, we cannot do that. We couldn't do the same thing that we did before. It wouldn't work. Mathematically, that would be incorrect. Now let's move on to some examples. Okay, so our first two are 2 root 6 minus 2 root 24. Now, like I said, we can't do anything to this just yet. We need to make these the same. And, well, we know how to do that, right? Root 24, we can change it. So, this remains 2 root 6. And now this will become 2 times root 24. We want to do what we've been doing this whole time. We want to rewrite it. 4 times 6, just like that. And from there, it simply becomes 2 root 6 minus 2 times square root of 4 is 2 root 6. And now they are the same root. Now we can subtract. But we're not fully done because we still have to multiply this. So we get 2 root 6 minus 4 root 6. And just like that, our answer becomes 2 minus 4, negative 2 root 6. Now let's do this one. Once again, they're not the same, but we can change the 54. So we get 2 root 6 plus 3 times, let's see, 9 times 6. That works. 9 times 6. That just becomes 2 root 6 plus 3 times 3 root 6. Bingo. Now they're the same. we get 2 root 6 plus 9 root 6, multiply 3 by 3. And our final answer becomes 11 root 6, just like that. A couple more examples. Okay, on to the next two. 3 root 8 plus 3 root 2. We want them both to be root 2. And we can rewrite root 8 as root of 4 times 2. And then from there, we can take square root of 4 to give us 2 root 2 plus 3. Just like that. Now they're the same. And multiply 3 by 2, we get 6 root 2 plus 3 root 2 equals 9 root 2. Now let's do this one. Now this one is a little bit different because now we have different ones in each. So we need to really think about this, and we need to think of a common one between them all, because sometimes you'll have a root of a function and you will be able to you can basically rewrite it in several different ways. So 3 root 18, we want our perfect squares, and the only perfect square that we can use here is 9 times 2. Okay, plus 3 root 12. Now root 12, the only perfect square we can really use is, well, 4 times 3. And finally 2 root 27, well, again, the only one we can really use is 3 times 9. So now from here, we want to do what we've been doing. Here, take the square root of 9, we get 3 times 3 root 2. Here we take the square root of 4, we get 2 root 3. And here we take the square root of 9, we get 3 root 3, just like that. Now from here we just multiply. 3 times 3 becomes 9 root 2 plus 6 root 3 plus 6 root 3. And from there, we can only add these two. We can't actually add this because it's different than the other two. So our final answer here becomes 9 root 2 plus 12 root 3, just like that. Okay, so now we're going to multiply our rational expressions. And well, we know, for example, 3 times root 5 is just written as 3 root 5, right? And if we have 3 times 2 root 5, that's just written as 6 root 5, right? But what happens when we have something like root 3 times root 5? Well, what do we do in this situation? And actually what we end up doing is simply this. Root of 3 times 5, which gives us root 15, just like that. And this is how we actually multiply our, what are they called, our rational expressions. If it's on the inside of our root, we multiply the insides. And if it's on the outside, we multiply the outsides. For example, just really quickly, if I gave you 2 root 3 times 3 root 4, well, in this case, we do 2 times 3, so 6, and then we take care of the inside, so 3 times 4. So it becomes 6 root 12, just like that. And now this isn't the greatest example because root 4 is actually 2, but if we were to change this to root 2, for example, then it would be 2 times 3 to give us the 6, and it would be 3 times 2 to give us the inside, to give us the other value. Okay, so on to some examples. Now, when dealing with examples, we can do one of two things. We could multiply them and then reduce, or we could reduce first. So I'm actually just going to go ahead and reduce first. This 20, we can change it to root 4 times 5, right? And well, root 4 times 5 becomes 2 root 5. Just like that. So then from here, well, we know negative 3 times 2 is negative 6. And root 5 times root 5 becomes 5 times 5 on the inside. But then it's just 5 squared, isn't it? Negative 6 times the square root of 25. And well, the square root of 25, we know it. Negative 6 It's 5. So our final answer in this situation is just 30. On to the next. We have root 15 times 3 root 5. Now here, there's nothing in front of this except like an imaginary 1. So 3 times 1 is 1. And then on the inside, it becomes 15 times 5. So we get 3 root 75. Now from here, again, we can simplify. 75 is 25 times 3. And 25 is a perfect square, so it becomes 3 times 5 root 3. And just like that, we get our answer, 15 square root of 3. On to the next few. Next up, root 9 times root 3. That one's pretty easy because we know the square root of 9. Just becomes 3 times root 3. And then, just for the sake of writing it properly, 3 root 3. On to this one. Now the 8, we're going to turn it right away into something else. We know that 8 is 4 times 2. So then immediately we get negative 4 times, let's see, what is that? 2 root 2 times the square root of 10. And from here, it is simply negative 8 root 2 times root 10. And from here, we just multiply what's inside. So it becomes negative 8 root of 2 times 10, which we know is 20. So I'm just going to write 20. Just like that. And well, here, again, we can simplify. It becomes negative 8. 20 is the same as saying 4 times 5. So we get negative 8 times the square root of 5 times 2, just like that. And then from here, it becomes negative 8 times 2, so negative 16 root 5, just like that. Couple more examples. Okay, our last two is root 12 times root 15, which we can write as root of 4 times 3 times root 15, right? And then if we take the 4 out, it becomes 2 root 3 times 15. Now from here, we multiply what's on inside. So 2 root of 3 times 15, and we get 2 times the root of 45. Now, we can simplify that once again. 2 times the root of 9 times 5. Just like that. And once we take the 9 out, it becomes 2 times 3 root 5, giving us a final answer of 6 root 5. Just like that. Finally, let's do this one. 4 root 8 can be rewritten, and root 2 cannot really be rewritten. So then we get 4 of 2 root 2 times root 2. Just like that, 4 times 2 becomes 8 root 2 times root 2. And we don't even need to put 2 times 2 in here. We know that a square root of a number times a square root of a number is the number. And to put that in algebra, root x times root x is just equal to x. We know that. Same way that if this was cube root and we multiplied it 3 times, just like that. So we know that root 2 times root 2 is just 2. And we get a final answer of 16 for this one. So now let's move on to dividing our rational expressions. Okay, so same way we use our exponent rules with fractions, where we just run it through, just like that, we do the same thing when it comes to taking roots. This becomes root 3 over root 4, just like that. And then, well, we know root 4, so it becomes root 3 over 2. That's our final answer here. Now, dividing, what are they called? Dividing rational expressions also has some other things to it. For example, with multiplication, we saw that root 3 times root 4 equaled root of 3 times 4, right? Which is root 12. And if we're dividing, it's basically the same thing. It's root of 3 divided by 4. For example, if we have root 6 divided by root 2, this simply just becomes root of 6 divided by 2, which then simplifies to root 3, just like that. And that's how we divide our roots. It's the same thing as multiplication, except division on the inside of the bracket. Okay, now let's talk about the final part of the video. When we have rational expressions in our denominator, that is not necessarily permissible. We're not really supposed to have that. And the way we get rid of it is we multiply essentially by 1. Because when we multiply something by 1, we don't really change it. And this is actually used a lot in math. The principle that a over a is equal 1, where a is any number and the other a is also the same number, this is used almost all the time. And it's used to change stuff up, to prove certain things every here and there. And it's really important to know. Now, here's why we do this, and I'll show you what we do. We multiply by root 2x over root 2x. We multiply both the numerator and the denominator by this value. So why do we do that? Because as I said earlier, root x times root x is equal to simply just x, right? So that's basically what we're doing. We're multiplying root x by root x. So from here, all we do is simplify. So 8 times root 2x becomes 8 root 2x, and root 2x times root 2x just stays as 2x. Now, don't forget to simplify. Here we have a 2 and here we have an 8. This can be reduced. That can become 1, and this can become a 4 to give us a final answer of 4 times root 2x over x, just like that. Now, it changes up just a little bit, and I'm skimming over this mainly because you're not really going to come across this too often, but it's very important to know how to do it. And the other scenario is the following. 5 divided by 3 minus root 7. Well, let's try what we just did. We multiplied both the top and the bottom by root 7, right? So then it would become 5 root 7 over 3 root 7 minus 7. Well, we still have a root in the bottom, don't we? So that's not how we do it. Okay, well, what if we tried multiplying the top and the bottom by this whole thing? Okay, let's try that. 3 minus root 7 over 3 minus root 7. Now let's multiply. So 5 times 3, 15 minus 5 root 7 divided by 3 times 3, 9 minus 3 root 7 minus 3 root 7 plus 7, just like that. Okay, now let's simplify this. And we get 15 minus 5 root 7 over 9 minus 6 root 7 plus 7. Okay. We still have a root in the bottom. So what do we do to get rid of it? Because we don't want any roots in our denominator. We just don't. So what do? Well, here's what we do. We simply multiply by the opposite sign. Just like that. Notice how this is a minus and this is a plus. And the reason we do that is because if you've gotten this far in math, this is called a perfect of square, a difference of squares. It's basically a minus b times a plus b is equal to a squared minus b squared. And the reason we do this is because, as I just showed you in the other one, a plus b squared, which was essentially multiplying it by 3 minus root 7, a plus b squared is equal to a squared plus 2ab plus b squared. This 2ab is what was the problem for us. We still had that middle term of negative 6 root 7. That was the problem. But when we do it in a difference of squares, there is no middle term. It just becomes the first thing squared minus the second one squared. So that's exactly what we do, and it works. So this becomes 5 times 3 is 15, 5 times root 7, so 15 plus 5 root 7. And it's being divided by, well, 3 times 3 becomes 9, 3 times positive root 7, and then 3 times negative root 7. And then negative root 7 times positive root 7 gives us negative 7, just like that. And you'll notice that positive 3 times root 7 minus 3 times root 7, it's the same term. These simply zero out. And we get 15 plus 5 root 7 over 9 minus 7, which can be reduced to 15 plus 5 root 7 divided by 2, just like that. Anyways, guys, I hope you enjoyed that video. If you want me to do more examples, anything like that, if you want me to cover anything again, if you need anything at all, leave it in the comments below. I'll be happy to help you guys with any math subjects at all. Hope this helped, and have a great day. Peace.